Hello friends, welcome to this Editronics channel. Today we are going to look at how an LED lamp works. This type of lamps, whether ceiling or most types of lamps that are very commercial today. What is its difference versus LED bulbs? And can these types of lamps be repaired? We are going to uncover it to look at how it works, so stay until the end to see how LED lamps work. Here I have this lamp to uncap it because it really started to oscillate. It started to blink. Here we see this brand, a normal generic brand you can get in the market. It's nothing special, and we see two little controllers or two regulators. In this case here we see this one that says Sapphire. Let's see if we can focus on an 18-watt LED driver, and it says it works. From 85 volts to 265 volts between 50 and 60 Hertz, and delivers a current of approximately 280 milliamps for a DC output load that can control between 45 and 72 volts. Like this, it's possible that these types of dimmers can, shall we say, calibrate to any type of lamp in reality. Let's uncover them and let's see what you have here. Internally, these lamps only have this plastic, and we see all the internal LEDs. In this case, this little lamp that is here, I had it on the ceiling and it began to swing. As I mentioned, it's just a matter of disconnecting. Look, there's no loss when it comes to putting it back together. Look on this side, it doesn't fit on this side if it fits, because it has a polarity. In this case, here I have this one that was like this, and due to use, in about 1 year, it started to fail. The LEDs did not burn out. I must only clarify the controller. The fact that it is turned on at No.4, which is the one that is used the most, since for logical reasons, the protective box tends to melt. Look what happened. The other one has less use time. That is, they are installed in a remodeling I did in my house. They have the same purchase time, but like this one, they are used less. That's why this one is a little like this, but this one is used more, and that's why look how it turned out now. What does this have internally to make a controller? On this side, it is taking out the voltage that depends on the LED lamp. We are going to look here to see if we can visualize the data, and here it tells us that it is also a white light Sapphire brand lamp, which ranges between 18 watts and has LED technology between 85 to 1065 volts of voltage. From entry to exit, he says he has 20,000. In other words, it supports 20,000 hours of use, but it doesn't tell us the voltage it supports internally. That's the only thing that's not clear here. Well, in this case, what the controller has is not much to be more specific. It is a simple source. Before there were capacitive sources in LEDs, not now. Now they are sources. It must have a diode bridge and two capacitors. Let's see if this is true by turning it around. Look, this capacitor is inflated. That is the oscillation. We can already see that there is a failure of the capacitor. And at the output, let's see a little inflated, not much the green one. This large capacitor is 10 microfarads at 400 volts. We are going to rotate this one. It has polarity. It is a negative electrolyte. And here we see the other capacitor. This one is of 3.3 microfarads at 250 volts, and we see here in electronics, we do indeed see a diode bridge. There you can see a diode bridge, the controller or driver and the protection diode. That's what we can visualize here. Through these cables, the phase and neutral arrive, in this case, in my country 110 volts, and here it says, look, line and neutral. The neutral passes through one of the phases, sorry for the diode bridge lines, and here we see the other line that comes to see here below and connects to the other input then. The two direct wires of 110 reach directly to the diode bridge, then in the diode bridge it comes out and then connects to the capacitor part directly between plus and minus. In other words, this capacitor receives approximately at its terminals a voltage that depends. It can be whether it is a 110 or 220 line. It will be the peak voltage that this component delivers, or rather stores. How do we get that calculation? It's pretty simple. Let's take a calculator. Let's put that over here. And the way to calculate it is equal to the following: the voltage that comes out to the output of the device after a diode bridge. We are talking that in my case it would be BRMS over 0.707 or by root of 2, which is the same story. In this case, we are going to assume 120 0.707 in this case. In the capacitor, when it is working, there is 169.7 volts peak. Now this capacitor, since it does not store much energy, because it is 10 microfarads, there will be a lot of curl, and that curl will be that at certain times. Fluctuate, that is, it may be a little less, but the limit will be 170, that is, the voltage that passes will not be 100% pure. If we can observe here, after this goes to the diode bridge, here there is it a notch? Yes, it's a notch. It looks like it was broken, but it's not a small notch, and this is the diode bridge, output purification capacitor. And from the positive line, there's a Schottky diode that's connected in reverse. From what I see, let's see if some type of voltage passes through here at the bottom. No, nothing else happens on this side. Surely there must be a line perhaps below the diode that powers the integrated. So, what these types of sources do is generate a voltage that is going to be induced on this small transformer, and what this transformer is going to do is take out the voltage here at the terminals, which will depend exactly on the number of LEDs we have. I can explain if this lamp, for example, had maybe, I don't know, 20 LEDs, and all 20 LEDs are connected in series. This will make the lamp illuminate perfectly without any inconvenience, because the sum of all the LEDs will give the total operating voltage. In the respective case, it would be 20 LEDs. Let's say, because most LEDs are almost at 3 volts, and the whites then would be 20 LEDs at 3 volts. We would be talking that this lamp is powered by 60 volts. It is just an example, and those 60 volts automatically, because they give me the consumption current and everything else. Now, how can I calculate how many LEDs this holds? It says here, consume or deliver 28,000 YY has 18 watts. So we know that the power is B times Y. So we're going to take 18 over 280 to the negative 3, because that's the current to know the voltage, what I told you. Look, it's 64 volts then. Here internally it has, I would say, 21 LEDs. So let's look at 21 by 3 volts. There it is. Look at the 63 volts. And this is going to make all the internal shape illuminate correctly. Because they are in series, there may be lamps that also have blocks. For example, one LED, let's put it this way. An LED block of 10 LEDs, other 10 LEDs, other 10 LEDs, and that in total, let's say, only consumes 30 volts. It may also be that those blocks are then connected in parallel, and this generates consumption for me. Now, these 18 watts does not mean that all of them are consumed by LEDs, because it will depend on how many LEDs we have, as I just mentioned. Now, it says 280 milli here. With this information, it is telling me that these LEDs that are internal are not necessarily all 30 LEDs are in series, because they are not in series. A very simple fact. An LED does not consume 280 milli in series. All the LEDs would have to consume 20. So inside this card, there must be LED blocks connected in series, and in turn LED blocks connected in parallel, so that it generates the 280 milliamps of consumption, and thus generates a lower voltage for me. Now you will say, well, but you just calculated 18 watts between 280 and half 64 volts. Yes, but let's remember that this controller says that it can have control voltages between 45 and 72. So I can have different settings until I can get to about 18 watts. Doesn't mean I have to consume them all. This internal card that we see here has that ability to receive all the voltage. This small integrated is responsible, let's put it this way, for regulating, controlling, and adapting to the voltage of the number of LEDs that we have connected here. That's a big plus. Now, what are we going to do? I'm going to uncover it so you can see exactly how it works internally. It was simple, put a force on it, but minimal, because this is very delicate. This breaks. It has a guide here, and this guide wedges with this small space. So it's not a lot of force you have to put on it. Here you can see what the negative line and the positive line have. I see the negative line, negative here, negative here, negative here, negative here, and negative here. And it goes back and the sequence repeats. Now the positive line comes this way. It connects to these blocks, and that way they continue to connect sequentially. So these LEDs that we see here, actually as you see them, are not there. All in series, as possibly there could be others, but they are in blocks. For example, this may be one block of LED, this another block, another block, another block. Now if one of the LEDs fails and burns out, obviously those connected in series will be disconnected. In this case, we are going to do the following, as here I have the connector. Let's give it voltage. Let's start with a low voltage. For this case, I have this Ridden fountain that we have already done once. A tutorial reaches me up to 60 volts, 18 amps, and we are going to start calibrating the different voltages. So you can see, in this case, for simplicity, I'm going to start with more or less good. The controller says that. 45 volt output. So I'm going to start with precisely that minimum voltage to take a component first. I'm going to bend it here to connect it here in the connector and check continuity to see exactly what the output is. So here I have a multimeter. We place it in continuity and I'm going to see. This is the positive line. So if you can realize this is a way of measuring. So let's remember positive. Yes, positive, and I'm going to take the source, and here I'll connect the positive line ready, and the negative I'll just inject here. Here we're going to inject the voltage. I'm going to play here for this case. Well, we turn on the fountain. I'm going to start at, I said, 45 volts. And we place the set of 45 here in the source. We wait a moment and I inject the voltage. Look, already illuminated basic, but illuminated look ready. And the consumption really can't even visualize it on my source screen. It really is very short. And I'm going to raise the voltage. I'm at 45. We're going to see 46, 47, 48, 495 so volts. And the consumption is barely going on. $300 milliamps there or so. We can already see that the LEDs are illuminating perfectly, and we are like in that consumption range of 280 milliamps. I'm going to lower it more or less to 45. There it was at 50 volts. Yeah, give or take. I'm telling you, I'm going to lower it, see if I can get it up to exactly 50. It says 50.1 volts, draw 200 milliamps. Total consumption, about 1 watt. Ready now, what was it for me? This data helps me more or less know the voltage of the operating LEDs. In total, we see 91 LEDs that are connected to the circuit. So we see blocks of series circuits, and we see those series circuits that come back and they connect to other LEDs, and this way they do the whole installation. So each block of 5 LEDs receives about 2.5 to 3 volts. And then the other blocks, when added up, generate approximately the consumption necessary to activate the LED block. So I told them more or less with 50 volts. And if we are aware, that would be because the sum of the blocks in series, and that makes the circuit work described on a piece of paper, would be the following. We're going to put this over here, and what we have are little LED blocks. So I have example here 1, 2, 3, 4, and 5 LEDs. This line connects to the negative. Now another block comes out of this line. So 2, 3, 4, and 5, and the negative line comes out that is connected here with the positive, and at the end the last block to read is the positive, and here another packet will come out, another packet, and so on. We generate depending on the number of LEDs, since obviously the total consumption works this way. I have the diode bridge that goes like this. I have an alternating, I have a negative. Here the 110 volts enter, assuming that was the case. The positive, here I have the capacitor plus minus, in this case 10 microfarads, and I think it was 400 volts. Yes, 400 volts. And from this side, the integrated circuit that will be connected together with the small transformer is already detached. So let's just say here comes the transformation cap. From what appears here, it looks like it's ferrite. Yes, the transformer is made of ferrite, so they are dotted lines. They are not continuous lines, and at its output we see here comes the transformer No, it is actually in coil configuration, not in transformer configuration. The design is bridged, the two entrances and the two exits. You can watch it here. Look in. The connection is therefore not in transformer mode. Look, two inputs, two outputs. They bridge them simply to use the coils between the circuit, and then at the output we see here the purification capacitor that comes out of this is the negative and the positive comes out. And this positive? Well, here you can't see because there are some tracks at the bottom, but it seems that the capacitor coil comes out and then it goes to the adaptation output. In conclusion, if I feed this card to 110 volts here, it will generate the voltage limit. In this case, it would be 72 volts. That would be the limit here, but the moment I connect the LEDs, this electronic circuit is coupled to the overall LED consumption voltage, and it's regulated. That's the advantage of these types of fountains. The old sources, the old capacitors worked, but without regulation, it only worked with ceramic capacitor resistors and did the control. In this circuit, they are already a little more elaborate and will vary depending on the brand. There are much better elaborate circuits. Better designed and with better functionality among them, I can consider the Philips brand to be a pioneer in this sense in the high durability electronic design of left controllers. Now what we're going to do is look at the integrated on the internet, see what it tells us according to the crude plan I just pulled out. It is not a very precise plan, it is just my appreciation as an engineer based on the experience I have achieved. In this case, the integrated one, looking at it here in the microscope, is reference BP2866D. So we go here to the internet and we are going to look for this reference, for example, here with what he is integrated, and I get these montages, look at them here. There are several references. For example, there is this one with this diode bridge that, if you realize, it is basically like what I explained to you is the capacitor diode bridge. The LEDs come, in this case, LED blocks in series. Well, here it is in general, and in parallel is the capacitor, which is the 10 microfarads, and then comes the coil and the diode it has, and here we see the integrated. Here it is. For example, it tells me it is the data sheet. We're going to look at this data sheet. Obviously, depending on the references, how we can find the different data sheets, and each behavior will be unique. We can't generalize here. It says that it is an integrated precision book type constant control. That is a driver type LED controller. That works at voltage of 80 and 5A at 265 volts input for LED control, universal illumination that can work at 500 volts, that has internal MOSFET, it has a demagnetization system, it also has a JFET control to see it that way, and we see that more here. It says that the package comes like a shop, and we see here the circuit that I had already mentioned to you a moment ago. I also found another reference. For example, we see this reference that is only 2866. So there are many references on the internet. Depending on the driver, we can find more integrated. For example, we are going to click back, and we can see other integrations that also do the control. For example, I click here. Here's the 2861XJ. If you notice, there's no diode here. There's a direct bridge here. So returning as to the logic that I am explaining to you. That diode is what it is going to do, because it is like a kind of discharge from the coil so that the energy cycle is carried there, and the lamp may not remain oscillating. Internally, we see that he has the internal MOSFET. Why do I say he has the monster? Because it has the drain. Obviously, also the JC also have gate drain soles. And here's a no connect pin, high voltage pin that says it supports up to 500 volts, or a no connect pin, a C sign pin that I imagine is like some internal species to make sense. Anyway, but this would be the plan. And now look at the rough sketch I made. Diode bridge capacitor, the integrated. And initially I said it was a transformer, which I was wrong. Then there is the coil and a capacitor, more or less. That was like the idea it gave me of the circuit. But in conclusion, I already found the plan. Were you able to find the manufacturer? Can it really be, let's put it this way, repaired? They are found integrated into AliExpress. Finally, we can repair an LED lamp. Yes, under the following criteria. First, the soldering an LED with cotton is complicated and you have to literally destroy the LED that is damaged. Melt it with cotton, and then to place the other LED you have to place tin in paste and heat from the bottom, possibly with the gun, or it is most advisable to have an iron even if it is a closed iron. Place the LEDs. Why? Because this is aluminum, what's here. So these LEDs are supported on the aluminum base and at the same time have the conductive track that is the copper layer. So it would be best to have these LEDs down here. Heat the iron. I imagine that the temperature of these LEDs, sorry for that of the casting paste, must be greater than 183°, because otherwise with the heat that this generates, they could melt and detach. So I imagine it must be 183 to 210 degrees approximately. The tin in paste then to remove? Yes, you could use a heat station or a cotton, but from experience I tell you that I have tried to change some LEDs from some lamps that I have had. And with the mere heat of the station, they melt. So from what I see, they are melted, they are welded thanks to plates. At the bottom, they are strategically located, and by heat, obviously the tin is collected, and that way we could repair or change them. Is it worth making the change? Really, yes. If you get the LEDs that are, it is not complicated to find them on AliExpress, but in your country, it may be difficult, and you have to bring, and not one but 50, 100 LEDs to be able to repair them. Now the card is easy to repair. If the integrated circuit is damaged, then you would have to bring the integrated circuit. But not all controllers have the same integrated circuit as I just indicated. There may be different ones on the market. This capacitor can be changed. The other capacitor can be changed. And in my case, what I would do is resolve all the pins to suddenly prevent false contacts from causing the circuit to oscillate and finally maybe change. What is the coil? Although the coil is simply a system to generate a constant current. The diode could also be changed. The God bridge could also be changed. Can it be repaired? Yeah, having the tools. Nowadays it is not quite expensive, but I think we would be doing a favor to this world that is contaminated with a lot of electronic waste, so we can repair it. I hope this tutorial on how LED lamps work have been to your liking, and let's learn a little more every day about how things work. Click like, share. See you until next. Bye bye.